The bee's honeycomb is a marvel of natural engineering.
They have got plenty of honey.
Everything they need is here. It's a place to raise their young and store their food. And it's all made from wax, a substance so labour-intensive that the bees have to fly the equivalent of 12 times round the earth to produce a single pound of it.
This almost looks man-made, manufactured. I mean, it doesn't look like something from the natural world. The precision, the fine straight lines that they've created is extraordinary.
Right. It's an engineering wonder for sure.
Look at that, it's perfect. Hexagons here.
Yeah, it is amazing. They've just done it for thousands and thousands of years. They were born to do it. They just instinctively know that this is the shape of their home.
But there's more to the bee's behaviour than raw instinct. There's another reason why they build in hexagons. And to reveal that reason, we need to turn to the universal language of all nature, mathematics. The bee's primary need is to store as much honey as they can while using as little precious wax as possible.
The bee's honeycomb is an amazing piece of engineering, but why have they evolved to produce this hexagonal pattern? Well, actually, they don't have too many choices. If you try to put pentagons together, for example, they just don't fit together nicely, or circles leave lots of little gaps. If they want to produce a network of regular shapes which fit together neatly, then you've really only got three options. You can do equilateral triangles, or you could do squares, or you can do the bee's hexagons. But why of those three does the bee choose the hexagons? Well, it turns out that the triangles actually use much more wax than any of the other shapes. Squares are a little better, but it's the hexagons which use the least amount of wax.
It's a solution that was only mathematically proven a few years ago. The hexagonal array is the most efficient storage solution the bees could have chosen. Yet with a little help from evolution, they worked it out for themselves millions of years ago.
So like everything in nature, bubbles are just trying to economize. They're trying to get as small as they possibly can. But in the case of bubbles, they can do it perfectly. A single bubble in the air is always a sphere.
At first sight, it seems obvious that the bubble should be round. But why is the sphere so special? The sphere is one surface, no corners, infinitely symmetrical. Of all the shapes this bubble could be, the sphere is the one with the smallest surface area, which makes it the most efficient shape possible.
And it is because nature loves to use her resources effectively that we can see spheres everywhere we look. The Earth is round because gravity pulls the planet's bulk into a ball around its core. Water forms into spherical droplets. The shape minimizes the amount of surface tension needed to hold the droplet together. And a spherical shape gives simple life forms, like this Volvox plankton, optimal contact with their surrounding environment. But not everything is spherical. And because bubbles are so thin and flexible, we can use them to create other shapes.
So a single bubble in the air is always a sphere. But if they touch each other, they can save material for both of them by sharing a common wall. And so they do. If they can save surface area by taking advantage of their environment, they will.
So when you've got just one bubble, the sphere is the most efficient shape. But as we add more bubbles, we see the geometry changing. So in this case, we've got 4 bubbles, and you can see them meeting at a point. But put a shape in the middle, we don't get a spherical bubble. We get, in fact, a little tetrahedron. With 4 faces, they're not exactly flat, they're parts of spheres. But each time the bubbles are trying to find the most efficient shape for the arrangement of bubbles. So now we've got 6 bubbles, we've got a little cube appearing in the middle. This is nature's laws at work. The universe is always trying to find the most efficient solution it can. And as we pop them, the bubbles change, finding the most efficient, until we're left with a sphere again.
It has no choice.
But what's most remarkable is that those solutions are so often neat geometric shapes.
Wow, that's a dodecahedron. That's fantastic. And they're almost perfect pentagons, aren't they? That's really surprising. They're not bulging really very much at all.
That's right. That's right.
So 12 bubbles around make 12 faces, and the most economical shape that they can make, the lowest energy, is the dodecahedron in the middle.
Yeah.
The soap bubble reveals something fundamental about nature. It's lazy. It tries to find the most efficient shape, the one using the least energy, the least amount of space.
And it appears there are fixed rules about how it finds these economic solutions.
The bubbles are incredibly dynamic, but each time one pops, they're always trying to assume the most efficient shape, the one that uses the least energy. And what they're doing is trying to minimize the surface area across the whole bubble structure. This beautifully illustrates one of the fundamental rules of bubbles, which is 3 walls of a bubble will meet always at a 120-degree angle. But if we in fact make each of the bubbles the same size, a rather magical shape starts to appear. The hexagon.
And when you pack lots of hexagons together, the pattern that spontaneously emerges is the familiar sight of a tightly ordered honeycomb.
So when we see that pattern at the heart of the beehive, it is in fact echoing some of the fundamental geometric rules of the universe.
But it was the Greeks who first took this innate fascination with shape and turned it into a subject of its own. They believed that by understanding its principles, they could describe the whole world. And they gave a name to this new idea, one which meant measuring the earth. They called it geometry.
The mainstay of Greek geometry was the discovery of 5 perfect shapes now called the Platonic solids, after the Greek philosopher Plato, who believed these were the building blocks of nature. So we've got the tetrahedron with its 4 faces, the cube with its 6 faces, the octahedron with its 8 faces, the dodecahedron 12 faces, and the most complicated shape of all, the icosahedron with its 20 faces. Today, these are more commonly known as dice.
But most surprisingly, these are the only 5 shapes like this that can possibly exist. They're the only perfectly symmetrical solids.
It's this almost magical symmetry which made the Greeks believe that these shapes were so important. They associated them with the building blocks of nature: air, fire, earth, the cosmos, and water. These 5 shapes built the natural world. It's very easy to dismiss this approach as naive. After all, it's clear that the world around us isn't made out of just 5 neat geometric shapes. But perhaps we should have more faith in this ancient intuition. Because by laying out the laws of geometry, the Greeks had in fact tapped straight into the code that shapes all nature.
But what's surprising is that we can find the same laws, not just in rocks and minerals, but deep inside ourselves. I've come to the Department of Chemical and Structural Biology at Imperial College in London. Steve Matthews studies how individual atoms are built up into living systems, like you and me. In this tiny wire loop is another crystal, But this time, it's a crystal of protein, part of the machinery of living cells. Just as it's possible to work out the atomic structure of the salt crystals with X-rays, we can deduce the shape of the protein molecules in the same way, though the results aren't quite so easy to interpret.
Now, I'd be hard-pushed to actually give a name to that shape mathematically. I mean, it looks like a blob. But
No, it doesn't have shape, but many of these blobs come together to form shapes.
So there's a huge amount of structure and symmetry in this protein. And,
Oh, yeah, definitely.
Yeah, and that's amazing. We've got a cylinder now. This is a real surprise to see geometry at work inside our bodies.
But evolution is, creates a very efficient process. So symmetry is a very efficient way of building, these types of structures.
So by a process of evolution, the biology has discovered that
Before us, yeah.
the geometry gives it the best shapes.
Yeah, that's right. But if you really want symmetry, then we can move over to a virus particle. This is...
Now, I recognise that. That's an icosahedron.
Yeah, that's an icosahedron.
This is one of the shapes the Greeks were obsessed with, but
That's right.
it seems that viruses are too.
That's right.
It's very striking, because the physical world, you somehow expect maybe salt crystals to be symmetric, but the biological world, everyone considers rather a messy one, but this is not messy at all. This is beautiful. The geometric shapes which we find at the heart of our cells are the most efficient that nature can produce. It seems like the Greeks could have been right after all.
But our world isn't filled with precise geometric shapes. It seems random, disordered. To find out why, we need to look to the sky and the crystals that fall from it. Snowflakes assemble themselves in the heart of frozen clouds and fall to Earth in a dazzling display. And if there's one thing we know about snowflakes, it's that they're all perfectly symmetrical. Physicist Kenneth Liebrecht has created a lab for growing and photographing these perfect crystals.
It's a cold chamber. It's actually cold on the bottom, very cold, about -40 on the bottom and about +40 on top.
So in some sense, this machine is trying to replicate what happens inside a snow cloud.
In a sense, that's right. I mean, it's not hard to grow ice crystals. All you need is cold and water.
In the freezing conditions of the chamber, we should be able to see the inherent geometry of the world emerging in front of our eyes as the crystals start to form.
And now, with any luck, we will see some stars growing on the ends of those needles.
As the temperature drops, billions of water molecules coalesce out of the vapor, spontaneously arranging themselves into these 6 pointed patterns. At least, that's the theory. But the reality turns out to be very different. As Ken found out, even in laboratory conditions, it's almost impossible to grow perfect snowflakes.
Molecular scale, it's quite perfect, but as the crystal gets bigger,
Yeah.
the atoms don't hook on always exactly the right way. So when it grows, how it grows depends on the environment, the temperature and the humidity. So it starts growing one way, and then it moves to a different spot in the cloud and grows a different way, and then a different way and a different way. And so by the time the crystal hits the ground, it's had a very complex growth history, and so it ends up as a very complex crystal.
If there are patterns, the chaos of nature, patterns that we're not aware of, but that we're attuned to on a subconscious level. This barn was home to one of the artistic revolutions of the 20th century. The painter who worked here had become disillusioned with conventional painting techniques. In fact, he stopped painting altogether and started spattering. He was as controversial as the art he produced. An arrogant, self-destructive drunk, and perhaps a visionary.
His name was Jackson Pollock.
The floor, you can still see, is covered in paint. What Pollock would do is to lay a canvas out on the floor. And then, often intoxicated, he would drip and flick the paint all over the surface. He'd come back week after week, adding more and more layers, more and more colours. The result was extraordinary. There were huge outbursts of abstract expressionism, just covered in paint, scattered all over the place.
Pollock's paintings sent shockwaves through the art world. No one had ever seen anything like this before. Life magazine declared him Artist of the Century. Others derided his efforts as the substandard dross of a drunken lunatic. But though Pollock's paintings courted controversy, they were incredibly influential. Not least because the apparent random squiggles are strangely compelling.
Many people have tried to copy Pollock's techniques, some in homage, others in attempted forgeries. But nobody seems to be able to reproduce that magic that Pollock brought to the originals.
Pollock's paintings seem to have captured something of the wildness of the natural world. But for a long time, no one could define exactly what it was that made his work so appealing. Until it came to the attention of artist and physicist Richard Taylor. His unique approach was to invent a machine that could mimic Pollock's eccentric painting style.
It's all based on this apparatus called the Pollockizer.
The Pollockizer?
That's lovely. Now, what it is essentially, though, is what's called a kicked pendulum. And as you know, a basic pendulum is very, very regular, like a clock. But at the top here, what you've got is a little device that can actually knock the string as it's swinging around. And that induces a very different type of motion called chaotic motion.
So this would be like Pollock's hand. This would be what he'd be trying to achieve with that sort of off-balance painting that we do.
Absolutely. So they're very similar processes.
It's very effective.
By recreating his technique, the Pollockizer is able to mimic one particular aspect of the artist's work. And that is that it appears more or less the same, no matter how closely you look.
You keep on seeing these patterns unfolding in front of you. And with a Pollock painting, all of those patterns at different size scales look the same.
This is a property known as fractal.
So if I took pictures at these different scales and showed them to somebody, in some sense they wouldn't be able to tell which one was the close and which one was far away.
Absolutely. So as long as you can't see that canvas edge, then you have no idea whether you're standing 30 feet away or 2 feet away. They'll both have exactly the same level of complexity.
More than any other painter, Jackson Pollock was able to consistently repeat the same level of complexity at different scales throughout his paintings. The fractal quality of his work appeals to us because despite seeming abstract, it actually mirrors the reality of the world around us.
When we started to actually analyze the buried patterns in there, this amazing thing emerged. Deep down hidden in there is this level of mathematical structure.
So there's this really delicate interplay between something that looks messy and chaotic, but actually it has structure and some underlying code hidden inside it.
Absolutely, and you can see it not only in his paintings, but you see it everywhere. You know, like a tree outside, you look at the tree from far away, you see this big trunk with a few branches going off. Superficially, they look cluttered and they look incredibly complex, but your eye can sense that there's a sort of underlying mathematical structure to it all. Pollock was the first person to actually put it on canvas in a direct fashion that no other artist has ever done. It really is the basic fingerprint of nature.
And that's what's most fascinating about Pollock's art. In creating works devoid of conventional meaning, he had in fact stumbled across something fundamental. Because fractals are how nature builds the world. Clouds are fractal because they display the same quality. giant clouds are identical to tiny ones. And it's the same with rocks. From appearances, you can't tell if you're looking at an enormous mountain or a humble boulder. And then there are living fractals, like this tree.
It's quite easy to see how fractal it is, because if you take one of the branches, it looks remarkably like a small version of the tree itself. And if you look at the twigs coming off the branch, they have the same shape. So you see the same pattern appearing again and again at smaller and smaller scales.
And trees also demonstrate the great powers of fractal systems. Their great complexity stems from very simple rules.
Now, the reason the tree makes this shape is because it wants to maximize the amount of sunlight it gets. Very clever, but also very simple, because you just need one rule to create this shape. What the tree does is to grow, then divide, grow, then divide. And by using this one rule, we get this incredibly complex shape we call a tree.
This is the same pattern repeating itself at a smaller and smaller scale. It's a rule that's easy to test. Grow a bit, then branch. Grow a bit, then branch. And before our eyes, a mathematically perfect tree appears. But just as you never get a perfect snowflake, you never get a perfect tree either. But allow for some natural variability, different growing seasons, the wind, an occasional accident, and the result is a very real-looking tree. And we find the same fractal branching system time and again throughout nature. This idea that the patterns of nature may be inherently fractal was pioneered in the 1970s by French mathematician Benoit Mandelbrot. This is his most famous creation, the Mandelbrot set. Its systems of circles and swirls repeats itself at smaller and smaller scales forever. And this infinite complexity was created from just one very simple mathematical function. Mandelbrot's quantum leap was to suggest that similar simple mathematical codes could describe not just trees, but many of the seemingly random shapes of much of the natural